stuff here. 3C, stationary points. So, stationary points, that is when the graph is stationary. Okay, that means it's not increasing, it's not decreasing, the slope is horizontal. Now we have 3 types of stationary points. Okay, so they're summarized in the table here. 3 types, they are local max, local min, and what we call non-stationary inflection. Stationary point of inflection. So, local max and local min can both be classified as turning points. So that word turning point is a little bit different from stationary points because it's when it turns from increasing to decreasing, right? Whereas you can see with stationary point of inflection, we're going to learn more about them in the next unit, but it goes stationary, but it continues its trajectory of increasing or it continues decreasing. Anyway, you're looking at the sign diagram and that's going to help you identify the type of stationary point. Okay, so all of them are stationary points where the slope is horizontal. So let's get straight into it anyway. Our process is pretty similar. We're going to differentiate and then we need to draw the sign diagram of the derivative. Okay, so we can use our calculator to support us, right? If I was going to draw this manually, I want to know when does it equal 0. I can factorize 3x. And so I've got the roots, right? The roots of the derivative function. All right, so you can G-solve them from the from your graph. All right, you can trace along. We can determine it manually. And then we need to go, when is it the derivative function? When is f dash of x positive and when is it negative? So, again, I can know this just through sort of intuition and from my understanding of maths, right? I'm going to look at this function and go, the derivative function is a quadratic and the a value out the front is positive. Okay, positive a value means it's a happy face. It's going to open upwards, which means it's cutting the x-axis like this, which means positive, negative, positive. Okay? If we have a negative a value, it's going to be the opposite. All right. If you're not sure about that, doesn't really matter. You can just refer to the graph. Okay, so that's the derivative function, and we're asked to find the coordinates and nature of all the stationary points. So what we can see from here is that the function, remember, this tells us about the original function. It tells us about the slope of the original function. And we can see it's increasing, and then it gets to 0, and it starts decreasing. So just trace it out. Increasing, decreasing. What's going on? There's a local max at x is 0. I'm just going to put 0, comma for now. And then I'm going to describe this one. We're decreasing until we get to positive 2, and then it starts increasing. So that's going to be a local min, all right? Decreasing goes down and then comes up. Local min at x is 2. All right. Now it does say find the coordinates of those points. And so if we want to determine the y value, all we're doing is taking the x value and putting it into the original function. Remember, we really emphasize this in the first unit. You put an x value in here, it tells you the y value. You put an x value in here, it tells you the slope. We want to know the y coordinate. We want to know the y value. When x is 0, plug it into the original function. The y value is minus 2. And when we plug 2 in, like we can evaluate it manually, we're going to have 8, take away 12, minus 4, take 2, minus 6. I mean, I might have stuffed that up, but we can process it. Now, I'm going to sketch the graph of it up here. X to the 3, take 3x squared, take 2. Not equals 2, take 2. Okay. Look at that. Local max at x is 0, y is minus 2. We can see it's increasing, it gets to 0, and then it starts decreasing. And then the local min at 2 and minus 6. Now, all of this information, you can just G-solve from the graph, right? You can just go to your graph, G-solve max, G-solve min, you've got the coordinates done. But the point here is that in the test situation and in the exam situation, it does say using an algebraic process, find the turning points. Okay, so that means you do need to differentiate, you do need to draw the sign diagram, and you do need to refer to the sign diagram. Okay, so that's example A. Let's move on to example B. We have x take 2 times x plus 3, power of 3 plus 4, y equals. Okay, so we need to differentiate this. We're going to use the product rule because we have u times v. All right, we have one function times by another. You could expand it all out if you wanted to. That's going to take a very long time. It's going to be much easier to just use the product rule. So we'll have u is x take 2, u dash is 1. V is x plus 3 to the power of 3. And v dash is going to be, we're going to have to use the chain rule here. We have a function to the power of n. So it's going to be n f of x to the n take 1 multiplied by f dash of x, right? Multiplied by the derivative of x plus 3 is 1. All right, we smash all that together. U dash v u v dash. And the 4, when you differentiate 4, that disappears, right? So that one's gone. Okay, so if we want to draw the sign diagram for this, I'm going to say it's probably much easier to have a look at our calculator. But let's talk about how we could do this manually. If we want to find when does this function equal 0, what we need to do is factorize something, right? We need to try and factorize it, and so then we can start applying the null factor law and so forth. And we can see x plus 3 and x plus 3 is common. So I'm going to pull the biggest factor of x plus 3 I can out the front. That's going to be x plus 3 squared. All right, so here we have x plus 3 to the power of 3. Here we have x plus 3 squared. So I'm pulling that out the front. What I'm going to be left with here is 1 lot of x plus 3. All right, I'm going to write it out and then explain why this is the case. Okay, if you were to expand this now, x plus 3 squared times x plus 3, that's going to give you it to the power of 3. And then if you distribute it to this term, that's going to give you that one there. So that's the correct expansion of it, the correct factorization of it. And now we can collect this in here, and then we can apply the null factor. Right? So I'm just focusing on the middle bracket now. I've got x plus 3 plus 3x take 6. And just collect that. So what's that? 4x. 3 take 6, 4x take 3. Alright, so we can establish the zeros from the roots of the sign diagram from this. I'm going to put down here, I think. So we have a double root at x is minus 3. And a single root at x is positive 3 on top of 4. All right, so cubics, we don't expect you to remember sort of the shape of cubics. Even I have a bit of trouble, but like it's something like this. If A is positive, it follows this shape. If A is negative, it follows this shape. All right, this is a cubic function, okay, because we have a squared multiplied by the linear factor. Nonetheless, let's refer to our graph, right? So I'm going to just graph the derivative function. I'm not going to graph the original. I've got x plus 3 squared. Let's delete all this. X plus 3 squared multiplied by 4x take 3. Okay, so what you can see is it's negative until it gets to this point, and then it's still negative until it gets to the 4 over 3. So it's negative, negative, positive. Okay? Now I expected that. I expected it, not that I expected it to be negative because I'm familiar with the cubic system, but I expected it to be the same either side of this because that is a squared factor, which means the function touches at 3. Because it's a double root, it touches the x-axis there. Okay, so I expected that to be the case. And then over here we have the, that's when it transitions to being above the x-axis. Okay, so remember, we're using the derivative function to make statements about the original function. So what can we see here? Firstly, we've got this. It's decreasing, it goes horizontal, and then it keeps decreasing. What's going on there on the function? So it's not a local max, it's not a local min, it's what we call stationary point of inflection. Okay, so we have a stationary point of inflection at x is minus 3. Alright, so to determine the y value, we would put x is minus 3 into the original function. Alright, so for now let's just say we've got stationary inflection at x is minus 3. And then we can see we're decreasing and increasing at the point 3 on 4. Decreasing and increasing, we have a local min at x is 3 on 4. Okay, so then let's say we do need those y values, we're going to need the original function. So I've intentionally avoided the original function so that now I can show you what we've uncovered just using the calculus techniques. So it is x take 2 times x plus 3 to the power of 3. And I'm going to have to zoom right out. Okay, I'm going to zoom in on this point. So that there is our point of inflection, okay? So what we can see from this, what this tells us is it's decreasing. You're walking down the hill and then it goes horizontal for a bit and then it keeps decreasing, okay? So that's not a local max, it's not a local min, it's what we call a point of inflection. Tomorrow we're going to learn about what that does to the shape of the graph. For now, when you recognize that, point of inflection. All right, and then stationary point of inflection. I'll come all the way down here, then you can see the local min there. And you can get the corresponding y value from the graph, right? Pretty messy. Okay, so that's that question, that's part B. Maybe I'll just mention this quickly, because I did brush over that, about how I can know it's going to have this. So remember, like a quadratic, if it's positive, it's opening upwards. So that means it's coming from above to below. All right, so that's if A is positive. If A is negative, it's going to have the sad face. For a cubic, this is the way it follows. You can think of some fancy way of remembering it. Because A is positive, it ends up positive, something like that. Anyway, it's coming from below to above, back to below, and back to above. Okay, so you can think it's got to pass. It's got from above, from below. Okay, it's touching, which means it's not passing back above. It's touching at that point, which means it's going back down. That's a double root, and then going back above. So you can sort of see that shape there. If I was to draw it like this. Okay, you can sort of see that shape from there, how I've understood that. Positive A value, there's A is positive 1, the number out front is positive 1, right? So that's how I've done it from there, otherwise just refer to the graph, use the graph to help you out. Okay, let's move on to the last one, which is sine of x, right? Okay, now sine of x, it tells us to find all, now we're getting quite good at this I think, we've done it in the test a bit, in the first year we've emphasised it. But we have the function y equals sine of x, and we want to know all of the turning points. All right, because it's a periodic function, there's an infinite amount of them, right? It goes on forever. So to find the turning points, we find the derivative. We're going to draw the sine diagram of the derivative function. So we're going to, well, what values of cos of x? What values of x make cos of x equal to 0? And again, like we should just be thinking about this, okay? That's the unit circle. Cos is the x value. Where is the x value 0? Here and here. All right, so what's the angle of those 2 points? Pi on 2 and 3 pi on All right, x is pi on 2 and x is 3 pi on 2. So we'll have pi on 2, 3 pi on 2. And, all right, we can refer to our graph again, but the cos function starts at the top and then it goes down and then it comes back up and then it goes down. It's a wave, right? So it's positive, negative. And this is going to keep going forever, this one, right? It's going to keep going forever, which means that point plus 2 pi in that direction and plus 2 pi in that direction, we're going to have the same thing occurring. So how can we best communicate that? We're going to have a local, all right, look at this, increasing, decreasing, local max. Now, I'm going to answer it if we had a constrained domain first, and then I'm going to talk about how we can extend it to all solutions. Local max at pi on 2, local min at 3 pi on 2 minus 1. Where am I getting these coordinates from? Well, the largest value sign it can take is positive 1, and occurs at the top of the inner circle, and then the lowest value it can take is minus 1, right? Again, you're just substituting that point into the original function. All right, if we want to answer it for all possible local maxes and minimums, then what we're going to do, we're just going to edit this a little bit, and we're going to have pi on 2 plus k2 pi 1, and 3 pi on 2 plus k2 pi minus 1, and then we'll say something like for all k is plus, for all k is an integer. All right, another symbol you might see pop up is this one. That means the same as for all. For all k is plus, so you can just have that messy mathematical script there, communicates with the same thing. But that's allowed us to say there's a local max every 2 pi lengths of these along, because it's repeating itself. There's a local min every 2 pi lengths of these ones along. Okay, excellent. So you can see not much of an extension, like we know when it's increasing, we know when it's decreasing, so local max. Use your calculator to support you. Really the only thing we've looked at is if the sign diagram has this form, or if it's positive and positive, then it's what we call a stationary point of inflection. All right, let's get into exercise C. 3.